Hi friends, welcome back to our channel Physics Tutorial. Today we are going to start a new chapter, that is Semiconductor Electronics, Materials, Devices and Simple Circuits. So in this chapter we will discuss classification of metals, conductors and semiconductors, intrinsic semiconductors, extrinsic semiconductors, PN junction, semiconductor diode, application of junction diode as a rectifier. So all these factors we will discuss in this chapter. Now we can start with the classification of elements. We know that from the smaller classes we have studied that the elements are classified into three. Okay, so here we are considering this on the basis of conductivity, how the materials are classified or how the elements are classified according to the basis of conductivity. And here we have three types of classification, that is metals or conductors and semiconductors, insulators. So these are the three classifications of elements. Clear? നമുക്കറിയാവുന്ന കാര്യമാണ് അല്ലെ, മെറ്റൽസ് അല്ലെങ്കിൽ കണ്ടക്ടേഴ്സ് ആണ്. ആൻഡ് സെമി കണ്ടക്ടേഴ്സ്, ദാറ്റ് മീൻസ് their resistivity will be intermediate. And insulator, so in the case of conductors or conductors or metals, we know that it will be the conductivity will be more. Right. So in such a case, the resistivity of the material will be very low. So low resistivity will be there for metals or conductors. That means it will conduct. So here the value of resistivity will be in between 10 raised to minus 2 ohm meter to 10 raised to minus 8 ohm meter. That 10 raised to minus 2 ohm meter num 10 raised to minus 8 ohm meter num edakkulla values ആയിരിക്കും. അതായത് metals അല്ലെങ്കിൽ conductors ഉണ്ടാവുന്നത്. അപ്പോൾ അതുകൊണ്ട് തന്നെ അവയുടെ conductivity will be more. Okay, so that point you have to remember. And then in the case of semiconductors, the resistivity will be intermediate. Okay, so in such a case the resistivity will be 10 raised to minus 15 ohm meter to 10 raised to 6 ohm meter. That means in the case of semiconductors, the resistivity will be between these ranges. Okay, 10 raised to minus 15 ohm meter to 10 raised to 6 ohm meter ആയിരിക്കും. Okay, then last case is insulators. Insulators എങ്ങനെയാണ്? Non conducting materials ആണ്. So in such a case the resistivity will be very high. Okay, so conductivity will be very low. So we can say that the value of resistivity lies in between 10 raised to 11 ohm meter to 10 raised to 19 ohm meter. So this is all about the classification of elements on the basis of conductivity. അപ്പോൾ ഈ ഒരു പോയിന്റ് ഓർത്തിരിക്കുക, കണ്ടക്ടിവിറ്റിയുടെ ബേസിസിൽ നമ്മൾ മൂന്നായിട്ടാണ് എന്ത് ചെയ്തിട്ടുള്ളത്, എലമെന്റ്സിനെ ഡിവൈഡ് ചെയ്തിട്ട് ക്ലാസിഫൈ ചെയ്തിട്ടുള്ളത്. സോ മെറ്റൽസ് ഓർ കണ്ടക്ടേഴ്സ്, ദെൻ സെമി കണ്ടക്ടേഴ്സ് ആൻഡ് ഇൻസുലേറ്റേഴ്സ്. സോ ഹിയർ വി ആർ classifying on the basis of resistivity. Clear? Now we have discussed the classification of elements on the basis of conductivity. But in the case of electronics, we will explain it in terms of energy bands. So we have to know what are different energy bands in solids. And we might have studied in chemistry each single atom. That means if you are considering an isolated atom, there will be certain energy levels. That means each electron will be having a discrete amount of energy, right, corresponding to different shells or subshells. So all those things that I think you might have studied in chemistry, right? So here we are considering a single atom. That means here we have only an isolated atom and the energy levels will be like this. So each electron will be having a discrete amount of energy. Here we can see the energy level is shown here, and each will be having that a specific energy, right? Discrete amount of energy will be here, that will be arranged like this. N is equal to 1 and here n is equal to 2, n is equal to 3, like that. Okay, but if you are considering a crystal or a substance, so what will happen there? In such a case there will be number of atoms, right? If you are considering one atom, this will be like that, each will be having discrete energy levels. But if you are taking a crystal or a substance, what will happen? There will be large number of atoms. So due to this large number of atoms, the energy value of electron will get modified due to the presence of the neighboring atoms, right? So each discrete energy level will be corresponding into an energy level, so that will split into a number of energy levels. So here we can see this is the case of an isolated atom, and if you are considering this as a material or a crystal, the element, that means the energy level will be like this. So that means each level will be split into number of energy levels. So here we can see first energy band, second energy band, third energy band, and then valence band, and above that we can see conduction band, like that. Okay, so here we are taking this energy along y-axis, and this band will be formed like this. Is it clear? Because of this neighboring atoms, only because of this neighboring atoms it will get modified, because there will be number of electrons and number of atoms in a molecule, or number of electrons increases in case of a crystal. Okay, so in such a case it will behave like a energy band. Okay, so we have to understand that there will be number of levels like this. So energy levels we can see there. And the one more thing is that the energy band is, it is a collection of energy levels. Okay, so there will be number of energy levels. The collection of energy levels are called energy bands. And here we can see that valence band is formed here. So what are valence bands? If you are taking a metal, we can see that there will be bounded electrons, right? And other rest of the electrons, free electrons, we will take as the conduction electrons, and the bounded electrons are called valence electrons. അതായത് ഒരു മെറ്റീരിയൽ എടുത്തു കഴിഞ്ഞാൽ അതിനകത്ത് ബൗണ്ടഡ് ആയിട്ട് കാണുന്ന ഇലക്ട്രോൺസ് ഉണ്ടാവും അല്ലെ, ബൗണ്ട് ചെയ്തിട്ടുള്ള ഇലക്ട്രോൺസ്. അത്തരം ഇലക്ട്രോൺസിനെ നമ്മൾ പറയുന്ന പേരാണ് വാലൻസ് ഇലക്ട്രോൺസ്, ബിക്കോസ് ദേ വിൽ നോട്ട് ബി ഫ്രീ ടു മൂവ്. ഒരു ക്രിസ്റ്റൽ എടുത്തു കഴിഞ്ഞാൽ അതിനകത്ത് ഫ്രീ ആയിട്ട് മൂവ് ചെയ്യാൻ കഴിയാത്ത ഇലക്ട്രോൺസ് ആണ് എന്ത്, വാലൻസ് ഇലക്ട്രോൺസ്. ബട്ട് ഇഫ് യു ആർ ഗെറ്റിംഗ് ആൻ എനർജി, അതായത് ഇപ്പൊ നമ്മൾ അതിനെ ഹീറ്റ് ചെയ്യുകയാണെന്നുണ്ടെങ്കിൽ, അല്ലെങ്കിൽ ഇഫ് യു ആർ ഗിവിംഗ് ആൻ എക്സ്റ്റേണൽ എനർജി, ദാറ്റ് വിൽ ബി ഏബിൾ ടു break their bonds and they will be free to move. Okay, so in such a case we can say that then it will be conduction electrons, but in the bounded state they will call as valence electrons. So this term we will use continuously. So just understand that bounded electrons are called valence electrons, and the band formed due to these valence electrons, that is called valence band here. And if you are considering the energy level, here we can see that there are two energy bands, that means valence band and conduction band. So in the case of energy band, there will be two specifications, that is there are two types of energy bands, that is valence band and conduction band. So if here we can see the diagram, energy level diagram. Here energy is taken along this y-axis, and here we have valence band and conduction band. Here the valence band means the collection of the energy band which includes the energy levels of valence electrons. So ഈ വാലൻസ് ഇലക്ട്രോൺസ് ചേർന്നുണ്ടാവുന്ന എനർജി ബാൻഡ് ആണ് the valence band എന്ന് പറയുന്നത്. And in the same way the conduction band is there, that means the energy band above valence band which includes energy levels of conduction electrons. So this is called the conduction band, and this energy band will be above this valence band, and which includes the energy levels of conduction electrons. So here we can see the conduction electrons, and here in valence band there will be valence electrons. Valence electron means the bounded electrons. They will not be free to move in the conductor. So here we can see that this valence band will be filled with this electron. So each will be having two electrons. In each energy levels we can see these two electrons in each level, right? Here two dots are there, that means the valence electrons are completely filled. And in between these two bands, that is valence band and conduction band, there is an energy gap. Okay, so that is called energy band gap, EG. So this distance, that means the energy gap between top of the valence band and the bottom of the conduction band. So here we can see this is the top of the valence band and this is the bottom of the conduction band. In between we have the energy band gap, that is EG. Okay, so this is all about the energy bands in solid. So we have to understand what are the bands in this. That means the valence band and conduction band, and then energy band gap. All these 3 points you have to understand from this. Now we have the second classification of elements, that is classification on the basis of energy bands. Here we can see different energy bands and how the materials are classified on the basis of energy bands. So usually we will use in electronics this classification. Okay, so on the basis of energy bands only we will classify in electronics. So here we can see metals or conductors. Here, if you are taking the energy band diagram, here we have the energy that is along y-axis, and here valence band and conduction band both will overlap. So in the case of metals or conductors, there will be no difference between this valence band and conduction band. So they will overlap. That means it will be very easy to conduct, because this valence band will be very easy to move from valence band to conduction band. So only when it moves to conduction band, it will be able to conduct, right? That is why the metals conduct easily. Here there is no energy needed to move the electrons from valence band to conduction band. So it will easily conduct. That is the peculiarity of this metals or conductors. So this diagram you have to understand, that it will be easy to remember about these 3 classifications. So here we have that valence band and conduction band both will overlap. Clear? And in the case of semiconductors, we have seen that the valence band and conduction band, they are not coinciding or they are not overlapping each other. Here there is a difference between this valence band and conduction band. This gap, that is called the energy gap. Okay, here we can see that this energy band gap, that will be less than 3 electron volt. So only a small amount of energy is needed to move the electrons from this valence band to conduction band. That is why it is called semiconductors. So intermediate energy level will be here, right? So if it is getting an energy level less than 3 electron volt, then it will be able to move the electrons from valence band to conduction band, and that will conduct. Okay, so that cases we will discuss in detail, that means semiconductors. And now we can move to the third classification, that is insulators. Here we have valence band and conduction band, and here we know that the insulators means it will not conduct, right? So here the valence band and conduction band are separated by a large distance, right? That is the energy band gap. Here Eg will be greater than 3 electron volt. So more than 3 electron volt we have to give for the material for getting this electron energy for moving from valence band to conduction band, then only it will conduct. So it is very difficult to conduct insulators. That means the energy band gap is too much high, so it will not be able to move the electrons from valence band to conduction band. Here this energy also you have to just remember, that is energy band gap means 3 electron volt. It will be more than 3 electron volt, and here it is less than 3 electron volt. So now we can conclude these 3 classifications. That means the classification on the basis of energy bands, that is metals or conductors, means the valence band and conduction band that will overlap. Okay, and in semiconductors what happens is that valence band and conduction band is not coinciding or it is not overlapping. There will be a energy gap between them. Okay, so that should be less than 3 electron volt, and here in insulators the energy band means the energy gap will be more. Okay, so that will be more than 3 electron. So here we have valence band and this is conduction band, and this will be more. Actually this will be a little bit more than the semiconductors. Okay, so that is all about the classification in energy band. So you have to just understand that what is conductors means insulators and semiconductors, and how we are getting an idea about valence band, conduction band and energy band gap. So no need to study the definition of this conduction band, valence band and all. We have to just understand that what is this, the concept. Okay, then it will be easy to move whenever we are discussing the next topics. Clear? Now we are moving to an important topic, that is semiconductors. So in case of semiconductors, we can see that there are two types of semiconductors, that is intrinsic semiconductors and extrinsic semiconductors. So intrinsic semiconductor means that will be pure semiconductor. So usually we will take germanium or silicon crystal as a semiconductor. So this will be having that pure form. That means we are not adding any impurities to such an material. We can say that this is intrinsic semiconductors. അതായത് pure semiconductors-നെയാണ് intrinsic semiconductor എന്ന് പറയുന്നത്. And extrinsic semiconductor means we will add some impurities to improve the conductivity. Okay, so such semiconductors are called extrinsic semiconductors, or we will say that is doped semiconductors. Doped means we will add some impurities, means some suitable impurity we will add to the semiconductor, and that will help to improve the conductivity. So such a semiconductor is called extrinsic semiconductor, that we will explain in detail. So you just understand that there are two types of semiconductors. First one is intrinsic and second one is extrinsic. In the case of intrinsic semiconductors, that will be pure semiconductors. So only semiconductor we are taking, and that is called intrinsic semiconductor. And when we add some impurities for increasing or improving the conductivity, that will be extrinsic semiconductors. And in the case of extrinsic semiconductors, there are two types of impurities we will add. Okay, so according to that we can name it as n-type semiconductor and p-type semiconductor. That depends on the type of impurity that we are adding. So just understand these facts, these are very important, and we have to understand the concept clearly, then it will be easy to study. Okay, so here we are just talking about intrinsic semiconductor. That means they are called pure semiconductor. So here we can consider a crystal. So we are taking a silicon crystal, and here we have this. Suppose we are considering this silicon crystal. Here we can see that each atom is covalently bonded, because here 4 free electrons will be there in the outermost shell of silicon. So here we can see that this 4 atoms that will be bonded with the neighboring atoms. Okay, that means it will form a covalent bonding, and here everywhere we can see that the covalent bonding is there. And suppose if we are increasing the temperature, this is the case at 0 Kelvin. Okay, because the temperature is 0 Kelvin, in such a case this will be, the pattern will be coming like this, because it will form covalent bond with each neighboring atoms. Clear? And suppose we increase the temperature, then what will happen here? If we are increasing the temperature means that the electrons will get energy for, yes, releasing the bond. Okay, so that will be able to break the bonds, and that will be free to move inside the crystal. So suppose here we have an electron, here we have an electron, and which is getting energy to release from the bonding. So what will happen? This will come to this side. That means it has released from here. So what happens here is that it will make a hole here. So we can say that if there is a deficiency of electrons, it will make a hole here, and this hole will be acting as a positive charge, and this electron has negative charge. In similar way, whenever we are increasing the temperature, what will happen here? Many electrons will be free to move. So that means it will break the bonds of the crystal, and they will be free to move inside the crystal. So whenever the electron is released, there will be a hole formed. അതായത് എത്ര ഇലക്ട്രോൺ ആണോ ഇതിന്ന് അതായത് ഫ്രീ ആവുന്നത്, അത്രയും ഹോൾസ് ആ ക്രിസ്റ്റലിനകത്ത് ക്രിയേറ്റ് ചെയ്യും. Now I am talking about only one electron, right? So in similar way, there will be many number of electrons, they will be released from these bonds, and there all a hole will be formed. So in the case of intrinsic semiconductor, the number of electrons will be equal to number of holes, because if another electron is released from here, what will happen here? If the electron is released here, a hole will be formed here, corresponding hole will be formed here. So in similar way we can see that the number of electrons in the semiconductor will be equal to number of holes. That is very important point. And at 0 Kelvin what happens is that it will be acting as an insulator. There will be no conducting electrons, and at 0 degree Kelvin that will be just as an insulator. Okay, when we are giving extra energy, that means when we heat the material, then only the electrons will be free to move here and electron hole pairs will be formed here, right? But what happens is that there is no extra electrons here, and the intrinsic semiconductors at 0 Kelvin it will be acting as an insulator. So that point you have to remember, that is very important point, and the electrons will not be free to move. Okay, so we can say that Ne, number of electrons, is equal to number of holes in this case, and total current will be due to this electron, means electronic current plus hole current. So I will be equal to IE plus IH. The total current we can take as the sum of these two. Okay, so this is about intrinsic semiconductor. Here there is no other impurities or are added to this pure semiconductor. So these are the pure semiconductors. Now we have to learn about extrinsic semiconductors. Extrinsic semiconductors means doped semiconductors, or some impurities will be added to the semiconductors, that we have told, right? So what is doping? That also you have to understand. Doping means the addition of suitable impurity to the semiconductor for improving its conductivity. So doping means addition of suitable impurities to the semiconductor for improving the conductivity. Okay, so here we will do that, how we are adding a type of impurity, and depending on the dopants. Dopant means the impurity atom are called dopants. So we are adding some impurities, means that impurity atom is called dopant. So depending upon the dopant, there are two types of extrinsic semiconductors. That is, first one is pentavalent impurity atom, and second one is trivalent. So here we are talking about pentavalent now, and after that we can talk about trivalent. So pentavalent impurity or trivalent impurity we are adding to this silicon. Okay, silicon or germanium we can take, and we are adding this impurity atom to this. Then what will happen here, that we have to understand. This is also very important topic, so you have to just understand that. So here we are considering a silicon crystal. Okay, and we can add a pentavalent impurity. Here, what are pentavalent impurities? Pentavalent means that is 15th group elements, or we can say that arsenic, antimony, bismuth, then phosphorus. All these are 15 group elements, or their valency will be 5. So such elements are pentavalent. Penta means 5 will be the 5 number of electrons will be there in their valence electrons. So that is why it is called pentavalent, and it is also called donor impurity. That I will discuss why it is called donor impurity. Okay, and here we can understand that this is the 15th group element. So whenever we add a pentavalent impurity, we can use any one of these methods. That means arsenic, antimony, bismuth, or phosphorus. So all these are pentavalent impurities, and here we can consider a silicon. Okay, so that is added to us. That means here we are taking this arsenic. So arsenic will be added to the silicon crystal. Then what will happen here? Here we can see at the center we have replaced this silicon with pentavalent impurity. So 5 free electrons will be there. So what will happen here? 4 electrons it will be sharing with the neighboring atoms. So 1 electron is free, right? So that 1 electron is given here. Right, so that will be free to move inside the crystal. So that will move inside the silicon, and it will conduct. Even when the temperature is 0 Kelvin, it will be able to conduct. Okay, so that is why we will say this as donor impurity. So we can call this impurity as donor impurity, because this is donating 1 electron. So whenever we are adding 1 atom to this, that means 1 arsenic atom, whenever we are adding to this, 1 electron is released here, right? 1 extra electron it is coming here. So that means it is donating that electrons. That is why we will call this impurity as donor impurity. And here we can see that the number of electrons will be more than number of holes, because this, whenever we add one atom, one electron will be formed. Like that we will add many number of atoms, right? So that much number of electrons will be free to move inside the crystal, and that will conduct. That is pentavalent impurity. So whenever we talk about extrinsic conductors, we have to understand that there are two types of extrinsic conductors. That is pentavalent impurity we are adding. This is called N-type semiconductors. So this is very important. Pentavalent or N-type semiconductors are here. Okay, so when we are adding a pentavalent impurity, we will call it as N-type semiconductors, and the pentavalent means 15th group elements are there, and they will be having 5 valence electrons in their outermost shell, and the elements are arsenic, antimony, bismuth and phosphorus, and this is called donor impurity. And one more thing is that here number of electrons will be more than number of holes. Here only the free electrons will be formed. Okay, so because there is one extra electron in this impurity atom. Clear? So this is very important. And now we have to discuss about trivalent impurity. That is the second type of extrinsic semiconductor. So now we have seen that in the case of pentavalent impurities, that means whenever we add pentavalent impurities, there were more number of electrons. So that means the majority charge carriers were electrons, and it was called N-type semiconductors, right? Now we have another type of impurity. That means here we are using trivalent impurities. Trivalent means 3 will be the valence electrons. So here we are taking the 13th group element for as the dopant. Okay, 13th group elements are the dopants. Here the dopants are indium, boron or aluminium. So indium, boron, aluminium etc. can be used to do doping with this silicon. Okay, so here we are considering a silicon crystal, and we have to replace one silicon with this. Here we are taking this indium. So indium atom we are adding here. Then we can see what will happen here. So in the case of trivalent impurities, what happens is that the outermost electrons are 3 only, right? That we have told. And this is called p-type semiconductor. So this is also very important. Trivalent impurities we are adding. So here we are getting that p-type semiconductors, and this is also known as acceptor impurity. And here the difference is that holes will be the majority charge carriers. That we can discuss how that will happen here. So here we are considering a crystal, silicon crystal we are taking, and here we can add an indium. Okay, so that we are placing at the center. So what will happen here? This has only 3 outermost electrons, right? So this will be formed with so the covalent bonds will be formed with these 3 electrons. Here we can see this 3 will be formed with the covalent bonds, and here one hole is there because one vacant space is there. Here there is no electron to form the covalent bond. So what will happen here? That is a hole will be formed in this place, right? So in order to fill this hole or a vacancy, what we have to do, another electron should move to this place. Then what will happen? Another hole will be created in this place. So that is why it is called acceptor impurity. That means this will accept electrons from other atoms. Okay, so whenever we are adding some more impurities, that means indium atoms we are adding, means that much holes will be created here. So this hole will act as a vacant space or a positive charge. So this will be acting as a positive charge. So electrons will be attracted towards this. And here we can see how many electrons we are how many atoms we are adding to that much holes will be created in this crystal. So this is called as the holes will be majority charge carriers and electrons will be minority charge carriers here, and this is called acceptor impurity. And one more thing is that we have to know that this is p-type semiconductor. The points you should remember is this is a trivalent impurity, and here 13th group elements are added to that: indium, boron, aluminium, etc. This is a p-type semiconductor. Then acceptor impurity is another name for this, and holes will be the majority charge carriers. So number of holes will be more than number of electrons. That is also very important. Number of holes is too much greater than number of electrons. Okay, so here the holes will be acting as the majority charge carriers. So even if the temperature is 0 Kelvin, due to this holes a current will be formed. Clear? Now we can have a quick review by considering the energy level diagram of all the cases. So here we are talking about intrinsic semiconductors, and in the case of intrinsic semiconductors, here we can see the valence band and conduction band. This valence band will be completely filled. Okay, and in the case of temperature 0 Kelvin, here we are considering the temperature as 0 Kelvin, and in that case we know that the total number of electrons will be equal to total number of holes. Okay, so what will happen here? Here we have to draw the energy level diagram, and it is very easy to understand. Okay, if you know the concept, it is easy to draw again. So here we can see valence band is completely filled. That means 2 electrons will be there in each energy levels, and the conduction band will be empty. Okay, so that is at 0 Kelvin, and when the temperature increases, what will happen to intrinsic semiconductor? That we can draw here. So here we can see that this is the valence band and this is the conduction band. Here energy is taken, and this is the case of temperature more than 0 degree. So here we can see that. Okay, so what will happen here? When the temperature increases, the electrons will be able to move from valence band to conduction band. Okay, creating a vacancy here. So here 2 electrons have moved from valence band to conduction band, means here that much means holes will be created, right? So that holes are here, but when we look into that, here we can see that if 2 electrons are moved, means 2 holes are created. That means the number of electrons will be equal to number of holes. Now we can consider the extrinsic type semiconductor. So here we are considering the n-type semiconductor. So in the previous case we have shown the valence band and conduction band. No, the similar way we can draw that also. So how we can do that? Here valence band is here and the conduction band is over here, and here we can see that at 0 Kelvin we are considering the semiconductor, right? And we know in the case of n-type semiconductor, number of electrons will be more than number of holes. So here the valence band will be completely filled, and some electrons will be there in the conduction band also. That why that conduction band is filled with not completely filled, partially filled electrons are there, right? Why there is electrons in the conduction band? Because we are adding that donor impurity, right? That is why we are getting that some electrons in the conduction band also. So we can see here that instead of means empty conduction band, here we are having some electrons. Okay, that is at 0 Kelvin. So that is only because of that impurities, and then that also you have to show here. So near to conduction band, just below the conduction band, we have to draw one more line here, that is the donor energy level. So due to that we are getting the electrons in the conduction band, and in similar way we can draw the same n-type semiconductor at more than 0 Kelvin, because when the temperature is increased, what will happen? Some electrons will be moved to the conduction band, leaving a hole there. Okay, so here we can see that here the electrons are moved from this valence band to conduction band and creating a vacancy. That means it will act as a hole, positive charge. But when we are looking into that, we can see that there are more number of electrons. That is why we can say Ne is greater than NH. That is, number of electrons are more than number of holes. So in a similar way we can draw the p-type semiconductors also. Now we have the energy level diagram of p-type semiconductor. Here we know that the number of holes was more than number of electrons, right? So here we have the energy level, here we can see number of holes will be more. Here 1, 2, 3, 4 are there, right? So when we draw this is at this is less than 0 Kelvin, right? Temperature is very less, and in such a case what happens, the conduction band is empty. Why that happens? Here we are doping with trivalent impurity, right? That was an acceptor donor, right? So what happens here, it was not able to complete the octet because there was a vacancy of, there was a deficiency of one electron, right? That is why there is no other electron in the conduction band. Here also hole was there. So what happens here, the similar number of holes we are taking here. Here we can see that holes are there, but there is no electrons or holes in the conduction band. So at 0 Kelvin, what happens here? No conduction is there, but in the case of more than 0 Kelvin, what happens when the temperature increases? What will happen here? Here, that due to acceptor energy level, here we can see a electron will be moving from this valence band to conduction band, right? So that will create a vacancy and that electron will be moved to the conduction band. So here conduction occurs due to this holes. So that here majority charge carriers are holes. So NH will be too much greater than Ne, number of electrons. So holes will be the majority charge carriers, and here we can see number of holes more than the electrons here in the conduction band. Okay, so here we can see this is the p-type semiconductor, and hope it is clear to you. Now we can conclude the video. So the rest of the portion we can discuss in the next video. Hope it is clear to you. Thanks for watching.